Okay, this is the second part of the second lecture. We're finally going to derive Lorentz transformation. Basically, we know the space-time coordinate dependence. Then from that, we can immediately derive the Lorentz transformation. Okay. Now, let's consider two coordinates that's with one the relative motion and the relative velocity is taken to be the x direction, or rather we choose the x direction to be the direction of the relative velocity. Then the transverse components of y and z are unchanged, and so the problem reduced to two component problem. How to change from x and t into x prime t prime. And if you want a formal argument of why the transverse component cannot change, I refer you to the side note 3 in chapter 2. So we're interested in how to express x prime t prime in terms of x t. We claim that must be a linear relation, meaning the coefficient a1, a2, b1, b2 must themselves do not depend on xt, in which we made the assumption that space is homogeneous and progression of time is uniform. It was the relation between xt to x prime t prime do not depend on where they are, when they take place. It's just the same. So therefore, if we write in the matrix form this x prime t prime into x and t vectors, the 2 by 2 matrix, the elements themselves do not depend on time. So if we call that matrix the Lorentz transform L, then this L matrix do not depend on x and t. Now let's set up the fact that these two frame references are in relative motion with velocity v. So it was x prime equal to 0. It was the origin of the red coordinates here, x prime, viewed in the x in the original O reference has position x equal to bt. So it was this distance here is vt. Okay. Now same way, the origin of the O frame, this point here, the origin here, x equal to t, is viewed in the x prime t prime frame. In the red frame, is moving to the left, so with x prime equal to minus vt prime. Okay. So if we plug these two conditions into so if we plug these two conditions into this transformation here, you find the coefficient a2 is related to a1, and coefficient b2 is also related to a1. Okay. So therefore, the fact that they are in relative motion with relative velocity v, the transformation is reduced to all three elements depend a1 except there's a b1. So uh, anyway, we need to find out what's a1 and b1 is. So we continue derivation. We already find for relative motion, the coordinate transformation is written this way. Or if we multiply out x prime equal to a1, uh, uh, because both have a factor a1 out, and t prime is b1 x plus a1 t. We take the ratio of these two equations. On the left-hand side, x prime over t prime. On the right-hand side, I also divide the numerator denominator by t, so I have a1 x over t minus v, and the denominator is xt over t plus a1. Now we impose a condition that if when the particle has velocity c, then it will be viewed as velocity, same velocity in the prime frame. So in other words, we could impose a condition when x over t equals c, x prime t prime also equals c. So therefore, the above relation become c times a b1 c plus a1, and on the other side is a1 uh, A1 C minus V. Okay. Now the CA1 and CA1 both have the term cancel. So right hand side only have B1 C squared, so divided by C squared, so B1 equal to minus V over C squared A1. So B1 also can be expressed into A1. So therefore the Lorentz transformation have every element has A1. So I factor it out, then I have 1 1 here minus V minus V over C squared. Okay. At the same time, I can write down the inverse Lorentz transformation by simply change the V to minus V. So I have uh, this expression. Okay. Actually, you can also argue why it had the same A1 from the principle of relativity, which again done in the book. Now we impose the consistent condition. So if this is really the inverse, then L times L inverse must equal to the identity matrix. So multiply them so they have A1 squared, but each have A1. And then I just multiply these two matrices. And they has to be equal to the identity matrix. And you can easily see, for example, this the first row times first column, 1 minus V squared over C squared, and the times A1 squared equal to 1. So therefore A1 must be when take the square root 1 over minus V squared C squared square root. And that's just the gamma factor, Lorentz factor we have been talking about. So therefore the Lorentz transformation is just this, just replace A1 by gamma. And this is the Lorentz transformation. We derived it. So therefore the new conception of time, the time can be coordinate dependent, allows the possibilities C prime equals C and leading to Lorentz transformation. Okay, and let's remember Lorentz transformation go to the new velocity rule and we'll get C prime. So therefore it's consistent. And notice now we have this new relation between inertial frame. Where does the Galileo transformation fit in? Well, it turns out Galileo transformation simply is the low velocity limit of Lorentz transformation. So if you take V much less than C, so therefore gamma goes to 1. If this term can be ignored, that's just 1. And so the Lorentz transformation is just this become 1, the coefficient become 1, and this the V over C squared goes 0. So that's just Galileo transformation. So therefore the relation between inertial frames are correctly given by Lorentz transformation, but if you take the approximation of low velocity, that recovers the Galileo transformation. This element point about all these transformations. You should, when we write something like this, x and t and x prime t prime, you should understand these meant to be intervals. They're not the labels of the event point themselves. Okay, so when we write x and t, we mean xt to the origin, x prime t prime to its origin. Okay, so it's intervals. So a good way to remind ourselves we're talking intervals, not just talk about the coordinates of some events. We prefer to write often, write as instead of x and t, we write dx dt. So this will be written this way. This will remind ourselves we're talking intervals. Now this is true not just to Lorentz, nothing to do with special Lorentz transformation. The same holds for rotation, same for Galileo transformation. They all really meant to relation among intervals. So again, we can have an exercise break. This time I can ask you, because the derivation of Lorentz transformation, you say, oh, it's some really new way of doing things. Actually, the same. It was you can derive the Galileo transformation that way. It was we can set up the fact for the Galileo Lorentz, we talk about the relative motion, two coordinates with v. That's the same. So therefore, the relation should be given this way. Remember, then we impose the C prime equals C, we get a Lorentz transformation. So instead impose the C prime equals C, if we impose T prime equals T, in which we impose absolute time, then you should show that this reduced to Galileo transformation. And also we've written down the transformation of the coordinates themselves, x and t. From this, you can also immediately figure out what's the transformation coordinate derivatives. Okay, so when we write del x, meaning this ddx, and del t will mean ddt, so on and so forth. We ask what is the transformation relates to the derivative in the original frame to the new frame. Okay, knowing the fact the coordinate transformation is given by this Lorentz transformation. I'll give you a hint. Because when del operator acting on x, the coordinates, you get the quantical delta, in the meaning that this is equal to 1 uh, when I equal to j, and not equal to 0 when I not equal to j. Okay. And the fact that the transformation leads to a quantical delta which does not change it with coordinate changes. So therefore, whatever the coordinate transformation of the del operator must undo the transformation of the coordinates. So therefore, this transformation must be undo whatever this does to the coordinates. Okay. Just from that, you can immediately write down the transformation for the derivatives. Okay, that's the end of the second part of the second lecture. And again, uh, just like the first part, you can uh, press pause and freeze this screen so you can think about it and work out the exercise before you turn off the. But I'm going to turn off here now.